Laurent Kneip graduated in mechatronics and got his PhD degree in 2013 from the ETH Autonomous System Lab, and he then served as a senior researcher at the Australian National University in Canberra at the ARC Centre of Excellence for Robotic Visions. His contributions at ICCV 2017 received the MAP-Wright Honorable Mention Award, a very prestigious honor in computer vision, for developing a new method for globally optimized image-based camera localization. And then he joined Shanghai Tech and was promoted to tenure associate professor in 2020. And he directs the Mobile Perception Lab. His research interests focus on many areas of geometry approach to computer vision, and most recently neuromorphic sensing. His open geometry vision camera calibration toolbox has been forked hundreds of times. Today, he will talk about how traditional geometry methods are adapted to event data and show some practical applications. Now, thanks for joining us today. Now you can.
Thank you very much for the introduction. And it's also really a great honor for me to have been invited today to present some of the work we have been doing in my lab. Yeah, you have been pronouncing my name correctly. Might even have been one of the best pronunciations you produced for all the names you mentioned today.
Is it Kneip? Is it Kneip?
Yeah, it's Kneip. Yeah.
Kneip.
It's a German.
Okay.
It's a German
Laurent
last
Kneip.
name.
Okay, thank you.
Yeah, I'm from Luxembourg, so it's a German last name. Yeah. I will present some of the work we're doing in my lab here at Shanghai Tech, the Mobile Perception Lab. As the name says, we are basically developing perception systems, SLAM solutions, spatial AI solutions for intelligent mobile devices. So we focus a lot on different kinds of sensors. We focus a lot on the different sorts of algorithms that we need in order to process data from such sensor systems. And then we also look at various applications in robotics and also augmented reality. So a lot of the solutions that we are developing are essentially focusing on a problem called simultaneous localization and mapping. And essentially the target is to produce solutions, as you can see here in this video, where we are continuously tracking a sensor, a camera through an environment, and also in parallel reconstruct some information, 3D information about the environment. In particular, in this contribution here, we are using semi-dense image processing, and yeah, this has been presented in TRO in 2018. Okay, so what we are doing since a few years is we are trying to basically make these solutions better and handle a few cases in which we have trouble. So we all know that if we use normal cameras, in particular just a single camera, we may face some issues, like the images may have certain latencies. We may have motion blur, especially when the illumination conditions are not so bad, not so good. And also we may have very challenging illumination conditions. For example, if we have a view straight into the sun, there might just be very bad contrast in our image. And so we have been asking ourselves the question, how can we perhaps use event cameras to the rescue here and address some of these geometric issues, such as simultaneous localization and mapping or camera pose estimation using event cameras. So I will focus primarily on this topic, which is the first part of my talk. Depending on how much time I have in the end, I will also show some of the more practical works that we have been doing over the course of the last 2-3 years. So let me start with geometric methods for motion and structure estimation with event cameras. The first work I want to show is something we presented in ECCV 2020 and also in TPAMI 2021, which is a method for globally optimal contrast maximization. So let me just very quickly refresh. I saw Guillermo is in the audience, so he might actually explain this a lot better, how contrast maximization is working. So essentially the idea is that if we have a space-time volume of events, and if we make the assumption that the events are all generated primarily by sharp contours or edges, appearance edges in the image, then if we understand how the events are moving over time in the image, which for example could be a function of some motion parameters, then we can unwarp the events along the trajectories along which they have been moving. And the result is something we call the image of warped events, as you can see here. And if the optimal motion parameters have been found, we have essentially arrived at a situation where these events exhibit maximum alignment. So the idea of contrast maximization is that we maximize the contrast of this image of warped events in order to find the optimal motion parameters. So this has been used for a number of works, and in particular, for example, optical flow or motion segmentation. These problems can be addressed using this technique. Let me show, there are various objective functions which can be used to express the contrast. Let me show one, which we can take as an example here, which is the sum of squares. Here is the objective that we're trying to maximize here. Essentially, here we have this warping function. It takes event locations and the timestamp of the event, and basically using then the motion parameters, it will unwarp events into the reference view, which then land on a certain pixel. So this is a pixel in this image of warped events. And here we have an indicator function, which basically gives us a 1 if the warped location is the same than this pixel. So what this is doing is that it's essentially counting for each pixel the events that are ending up on one pixel here in the image. And now we're summing all of this up for the whole image. And the important part here is that we're taking the square of this value. So obviously this then becomes a contrast measure, which is higher if events are more concentrated in fewer pixels. So this is relatively straightforward, but the issue is that in the literature, this has been used a lot, but it's primarily solved as a local optimization problem. And what we have been showing here through a number of experiments where we are essentially just changing the texture of the scene that we're looking at, or also slightly the motion that we're exhibiting here, it's very easy to show that this contrast objective is actually a non-convex objective. And therefore, it's also very easy if we, for example, want to continuously track the motion of the camera to at some point end up in a local optimum, which is no longer the global solution. So what we have been doing in our work, globally optimal contrast maximization, is we essentially have derived upper and lower bounds for the contrast objective, given certain bounds that we have on the warped location of our events. And these bounds in turn can be derived from our warping function and bounds on the motion parameters. So that part is generic and can change for any problem that we want to solve. But this work here is basically then providing a general upper and lower bound formulation for any kind of warping function, image warping function that we may want to use. In particular, we have derived the bounds for a total of 6 different contrast maximization functions, and evaluated this then also on a practical example. So here we have a small robot which is equipped with an event camera which is downward facing, and the image warping function here, of course, the camera is just watching at a planar scene. So the image warping function is simply given by a homography. And although we see here the rotation and the translation, in fact, they are continuous time functions of velocities here. And given these velocity parameters, which are our motion parameters here, and bounds on this, we see here omega and v in this equation. So these are the translational and rotational velocities, and maximum and minimum bounds on these values. We can derive the bounding box for the unwarped location of events, and we can tug this into our framework, and then by this basically derive the upper and lower bounds on the contrast maximization objective. So I'm not going to go through all the theory. This is a relatively longish proof. I encourage you to read the PAMI paper to see this result. I'm just going to show some interesting results that we have obtained. And in particular, here we have continuous motion estimation results for 3 scenarios in row 1, 2, and 3. And I want to draw your attention to the third column, where we see basically a bird's eye view onto the trajectories executed here by the robot. So this is in a reasonably sized room. In the first example, the robot is just having a motion along more or less a straight line. In the second example, the robot is moving along a circle. And in the third example, it's moving along some sort of a snake trajectory. And we can see, we're comparing this here against image-based alternatives. And we can see that due to the very strong optical flow that the camera here exhibits, we basically cannot get good results using traditional cameras. And we can achieve a strong result here with our event camera. In particular, we've also compared this against the gradient-based optimization. And we've also shown, I've taken out this result in the interest of time, but we've also shown that if we try to continuously track with a simple local optimization method, it will also eventually get stuck in local optima and diverge from the ground truth trajectory, whereas this result here gives us a much better result. Okay, so moving on to our next work, which we published much more recently, and it fits nicely into this context because it's also on contrast maximization. In particular, it's aiming at an extension of this method to 3D. So just going back to the previous contrast maximization method, what is the problem? Well, we need an image-to-image warping function. And for those who are familiar with 3D vision, they will know that such a warping function only exists if we're looking at a planar scene or if we have purely rotational motion. Now, the typical case is, of course, much more complicated. We may have arbitrary 6 degrees of freedom motion in front of an arbitrarily shaped environment. So if we want to design the warping function in this case, and we still want to do it based on image-to-image warping, then what we need is also a very high-dimensional parametrization, which includes the unknown depth of the scene. Now, that's not convenient to solve. So what we have done instead is we have tried to move this contrast maximization objective into 3D. And we therefore call this volumetric contrast maximization. Now here we can see how this works. What we have now is essentially a continuous time parametrization really of a trajectory in 3D. And we are no longer unwarping events in the image plane, but what we get as a function of this continuous parametrization is a continuous location or warping of the rays that correspond to each one of the events captured along this trajectory here. And now if we're casting those rays into a volumetric grid in front of a reference view, what we can again see is that if the optimal motion parameters are found, this density field here exhibits maximum contrast. And we can see an example here on the right side where we have moved an event camera around an office chair. And in the bottom row, what we see is the density field for wrong motion parameters. We can see that it's not having as high contrast. On the top, what we see is the density field for the correct motion parameters. We can see that this is much more, well, having much better contrast. So we also have a video on this result where we can see that we are effectively able to reconstruct here the continuous trajectory of a robot, which is here having a relatively simple trajectory, just moving along a circle. And what we get also as a side benefit then really is a 3D model of the environment. It's basically given as an implicit result through our density fields, because we just need to look at the local maxima in the density field, and then eventually this also gives us likely locations for 3D structure. I should mention that this framework is highly interesting because in contrast to other SLAM frameworks that have been proposed for event cameras, we are not doing an alternating optimization here. It's not a framework that alternates between tracking and mapping, but we really present a joint solution here for motion and structure, despite the fact that structure is represented implicitly here. So this is really interesting, and you can really consider this as the equivalent almost of bundle adjustment for event cameras. Okay, so I have one third work I want to present on geometry for event cameras. And we're really trying to go back to pose estimation. We were asking ourselves, okay, what does it mean to do relative exterior orientation computation for event cameras? If we have normal cameras, we have two views. Now with event cameras, of course, we have to move the camera before we see something. So intuitively for event cameras, exterior orientation computation is really something that we want to solve infinitesimally, and it means finding the speed of the camera. And so recently we have been looking into this, and we have been trying to really leverage traditional geometry in order to solve this problem. In particular, this framework here is feature-based. We're trying to leverage line features and then also trifocal tensor geometry in order to come up with novel incidence relations for event cameras that in the end will give us speed. So what happens is that the trifocal tensor is again, this is a function essentially of relative rotations and translations, and we again express those as time continuous functions of rotational velocity and translational velocity. And what we're having in the space-time volume of events, if we see a line moving here, it basically forms a small piece of a manifold here. And we really use then our continuous trifocal tensor relations in order to form incidence relations here with these small manifolds and give us constraints directly on the velocity. We call this the continuous event line constraint. Actually, that one is obtained by making certain simplifying assumptions. For example, the workshop is about fusion with IMUs. So here we assume that we are taking rotational velocity from an IMU that can be readily obtained from here. And therefore, it essentially then turns into a linear constraint for translational velocity, which is quite beautiful. And this work actually also currently sees some extensions in my lab, where we actually then putting this into a continuous tracking framework and doing really tight fusion with IMU. So that's going to come out relatively soon. Okay, so I've been rushing through this, so I have still a little bit of time here to show some of the more practical things we have been doing. Those are mainly tools for doing research on geometry for event cameras. And I'm going to introduce them here. They are partially publicly accessible, so hopefully that's going to be useful. The first one is dynamic event camera calibration. So we all know that when we do camera calibration, often what we use with event cameras is a static camera in front of a blinking screen. And this is unfortunately not always available. Sometimes our camera may also be mounted on a large-scale system, so moving a blinking screen in front of it is not very convenient. So what we are doing here is to, again, use a static pattern, and we are using circular markers here on this pattern. So if you move the event camera in front of this, we can really reliably detect these features here. And we can even use OpenCV, standard OpenCV camera calibration toolbox to get initial parameters for the extrinsics. And then again, what we add in the end is continuous time optimization over the trajectory parameters and the intrinsics. We can see here a result, how this works. Is really interesting because you can shake the camera quite aggressively in front of the chessboard here and use sequences as short as 2 or 3 seconds to get really reliable intrinsic parameters out of the camera. So it's also very time efficient to use this framework here. Another work I saw my student is in the audience. Hello, Gauling. I'm presenting his work here. He's, by the way, going to come to Zurich just in 1 or 2 months. He's going to spend a year there. So if you want, you can also get directly in touch with him when he's there. He has been recently proposing this work here called Vector, a versatile event-centric benchmark for multi-sensor SLAM at IROS this year. But it's actually going to be presented only in a week or so. And it's also presented in REL. So really what we felt is that there is a lack of data sets for research on event camera-based SLAM. So we built this, he built this cool rig here where we have a LiDAR, 2 normal cameras, 2 event cameras, a depth camera, an IMU, and then this is fully hardware synchronized. And we also have really made the effort to have very accurate ground truth with this. We captured really lots of data sets with this in the raw form, in the form before compression. This is 20 terabytes of data. So we have lots of sequences, both large scale, small scale, both with high dynamics, low dynamics, and also with very different illumination conditions. So feel free to have a look at this if you plan to work on SLAM with event cameras. I think this could be a very valuable resource. Something I was just thinking about, the previous work I mentioned on the speed initialization for event cameras, that was work done by another student, by a student called Xu Wanting, and she's also going to come to Zurich and spend a year there in the lab of Professor Mark Polleface. So you can also get in touch with her if you want. Okay, so yeah, again, this is about sensor fusion here. I have 2 very short things I want to show at the end. So
sorry, Laurent, you're out of time now.
Okay, then we're going to
so
skip
let's go to the discussion. Yeah.
Yeah, no worries.
Okay.
Thanks a lot for.
Thank you for that. That's really cool.
So thanks for the presentation. Yeah. So any questions from audience? Raise your hand. You have. Okay. Actually, I'm very interested in the data set you present, like the event-based SLAM. So I want to know, because I didn't see quite clear, what type of sensor do you have? Can you show it again, the table?
Yeah, so we have 2 Prof C generation 3 cameras. There is 2 Grasshopper cameras. We have a Kinect for depth. There is an Auster 128 beam LiDAR on it, an Xsense IMU. And then this at the bottom, the very 2 at the bottom, they are basically for ground truth. So we have had a bit of trouble to get a really accurate ground truth. What we choose in the end was a Faro laser scanner. So that gives us very accurate point clouds of the environment. And we are aligning this with the LiDAR point clouds. So this really allows us to get rid of the drift in the long-term drift in the trajectories and get very decent alignment for the trajectories with ground truth.
Yeah, that looks like a really cool data set, 20 terabytes on. Yeah, that's cool. In fact, I think Cornelia and Levy will talk about a different data set, which is this EVIMO, this independently moving objects where the objects are actually scanned ahead of time and then labeled. So these objects are moving around in the scene. But this is a related data set, but it's different, right? Because it's seen as static here generally.
Yeah, this is really more focusing on SLAM and pose estimation problems. So for these algorithms here, these data sets here, we have kept them static, yes.
Oh, there's a question from Larry Dong in the participant panel.
Okay, so Lyra, can you share your...
Hi, Professor. Can you hear me?
Yes.
Yeah, I have 2 questions here. The first one is about the depth estimation. We know the events are generated by the edges, but I think the edges always are more often between the 2 objects. So I think the depth is not unique or unstable here. I noticed there are a lot of outliers in some algorithms, such as EMVS. So is that a real problem in your research? Do you think the depth is is unstable here? And the second is the second is that I noticed there are limited SLAM using deep fusion for event cameras. We can see a lot of SLAM with RGBD or standard camera and event camera, but they are limited using MU, LiDAR, RGB event camera together. So is there any challenges to fuse all these sensors together?
Okay, so for the first question, actually a lot of our works have been primarily focusing on evaluating the accuracy of the motion, right? So for this, even if some of the part of the scene is not so well observable in terms of depth, then it doesn't really impact immediately on your ability to estimate the camera motion. But of course, I agree, like it is a problem, and it's not just with event cameras, it's also with normal cameras, right? If you try to do depth reconstruction and yeah, you use like these semi-dense methods, then often there is some ambiguities because you have depth discontinuities between foreground and background. So your depth estimation may sometimes not be that good. Actually, answering this question gives me very briefly chance to show this work where we actually do combination of depth camera and event camera. So we're using the time surface map and the edges in here to get this kind of semi-dense point clouds, and then we align this to track the camera. And there is this problem occurring here as well. So how we solve this, if we have edges in the time surface map, basically we need to search in a local neighborhood here in the depth map to make sure that we get the foreground pixels and bypass occlusions here. So there's some engineering tricks that we have to play in order to deal with those issues. What was the second question? If we can combine both depths and event camera?
Yeah, about the SLAM, yeah.
Yeah, I think there is no problem to this, right? We have been seeing lots of pairwise combinations of these sensors, and ultimately it should be possible to also put all of this together. I think our data sets, one of the target really is to design such frameworks, but yeah, it's mainly an engineering effort, right?
Okay, thank you.
Okay, so we have another person. So Suman, yeah.
Suman.
Hi.
Hi.
I was wondering about your work on contrast maximization in 3D. So I was wondering if there is any, if that method works well for particular motion models and doesn't work for others. Like
yes.
Do you mind going back to that slide? Do you mind going back to that slide?
Yes,
I don't know what number it was. Yeah.
Absolutely. So basically it's this one here. Yes. Okay. So I haven't been having too much time to talk about it, but yeah, something that what has to be said is that this is definitely a very, very challenging problem to solve, because event cameras are much more noisy in their data than regular cameras. So in this case here, what we have been doing in order to make sure that the result works better is we have really constrained the trajectories to be smooth trajectories on the plane. And that has helped really to get the results to converge better and to get more accurate results. I think if one has to really solve completely arbitrary, aggressive 6-degree of freedom motion, then using an approach like this here might still be very, very challenging. And definitely the addition of alternative sensors that, for example, sense depth or even dynamics like an inertial measurement unit may be very helpful to get things to converge.
I mean, it doesn't make sense not to use IMU because every one of these DVS cameras has an IMU on the back of it, right? And
True.
It's maybe a crappy IMU, but it provides good high frequency information. It has a lot of drift, has a lot of offset, but it definitely provides pretty good high frequency information. So it's senseless not to use it, in my opinion.
From an engineering perspective,
you get it for free. Yeah.
From an engineering perspective, yes. From a research perspective, sometimes we also want to understand what a single sensor actually can give us, right?
Yeah.
Okay, so any other questions?
We still have a couple of minutes left of this 10-minute discussion. I have a question. I mean, and Guillermo can also comment here. I never quite understood the difference between this contrast expectation, contrast maximization, and just lining up the events, which you can, obviously see in any 3D view that you zeroed around. Decades ago, we could observe that, but it's the same as computing optical flow. If you have the optical flow, you can also line up the events, right? Or am I missing something? It's equivalent to computing optical flow, local optical flow with some smoothness constraint, or am I missing something?
I think that the motion of the events in the image can be more complicated than that. So let me show this picture here to illustrate this. So if we're looking, for example, at how a line moves in the space-time volume of the events, and we have both translation and rotation, then it's not like really a motion pattern that is locally constant, right? In the space-time volume here, it really forms like a twisted manifold. And so
I see. Yeah.
The functions that are explaining the warping here, they can be even nonlinear. So they are not, it's not as simple as just finding optical flow, I think. So these motion models can sometimes be a bit more complicated.
But if the optical flow, I mean, you're thinking of a single optical flow factor at the start, which is not changing over time. But if the optical flow is continuously updated by the data, it seems, am I missing something? Isn't it, you can use that flow to also dewarp the event cloud?
Yeah, it depends on the length of the time volume in the end, I think, because if we just calculate local optical flow, then it's a bit. I think
noisy. It's noisy as hell, right?
It's often relying on locally constant motion assumptions. But if we are trying to process a larger window, a larger interval of events, then maybe the motion of the events can become a little bit more complicated.
Okay, and I think, Guillermo, this afternoon, you're going to discuss aspects of this in the context of stereo vision. Is that correct?
Yes, so I was not really thinking about talking about optical flow, but I could. I mean, in the 3D, it's the opposite. Is if you know motion, right? If you know optical flow, if you know the camera motion, you can warp the events to get the depth.
Yeah.
So it also works in the other direction.
Sure.
Okay,
Yeah,
we're out of time.
All right.
You can update the optical flow in real time, like say make the segment short enough. I think that you can get the continuous motion. Then you can, I think the same. But if you have longer, even a segment, then the optical flow maybe it's not same as the motion like the parameter, because my motion parameters can be like 6 DOF. That's very complicated.
Yeah, I think that to get accurate motion and depth, you need slightly longer intervals, right? It's from basic geometry, we know this because it's related to the question how large your baseline is. Yeah. If you just look at very local optical flow, then it's very hard to get accurate depth from this, right?
Yeah. Okay, so I think we can have a break now.